Yes, we're going to hear about a very ambitious topic, growth and evolution from Run1. So more than 10 years ago to the HL-LHC. And we're going to hear from Sharad. So take it away.
Thank you, Liz. So hi all, I am Sharad on behalf of CMS Collaboration. I will be presenting the growth and evolution of CMS offline computing from Run1 to HL-LHC. The agenda of the whole talk will be introduction to CMS offline computing and the growth and evolution in the three main sectors, which is distributed grid computing infrastructure, data management, and data production. So a little bit about CMS offline computing. So the data that comes into CMS offline computing is through two ways. It's the real data, which is coming from the experiment and the Monte Carlo simulations. All this data goes to the data centers, and then we do different data reconstructions over the WLCG, and the data is sent across different sites through the WLCG, and the final output data sets are produced. These output data sets, which are produced from production, are used by different analyzers to give the final analysis results. So the CMS offline computing uses typical 200K cores of Monte Carlo simulations and data reconstruction. And we help approximately more than thousands of CMS users to analyze the CMS data through the WLCG. So this whole graph is just to tell you when the Run1 started, when the LS1 is, because we will be talking in the whole talk in these terms of Run1, LS1, which is a long shutdown one, Run2, and as you can see, I have circled out that right now we are in the LS2, which is long shutdown 2. So talking about the growth and evolution of distributed grid computing infrastructure, during Run1, we used middlewares like glite, htcondor_g, and the gliding WMS softwares for scheduling jobs over the WLCG. And we started with the grid mesh topology. During LS1, the grid mesh topology was completed, and we also introduced the X2T endpoints for AAA. We also came up with the multi-core pilots introduction during LS1. During Run2, we completely shifted the whole dependency of grid computing to HT Condor and gliding WMS. We also switched to Singularity, which is basically removing all the operating systems dependency at sites. And we started doing advanced X2T endpoint monitoring. During LS2, we have been doing a lot of things, out of which one of the major things is the SiteDB to Quake migration. So we wanted to shift to Quake in order to in order to use a software which is coming through the collaboration, the WLCG community. And we started to do advanced monitoring of almost everything in grid computing through Monad Grafana. And we introduced partitionable slots in the global pool and started using HPC resources. We have different plans for Run3 and HL-LHC, which include improving the usage of HPC resources, heterogeneous computing using hardware accelerators, migration of certificates to tokens for authentications, and to complete the migration of the creamed computing element to HT Condor computing element. So this is a very high level overview of the CMS submission infrastructure, where we have the production SCADs and the analysis SCADs, and they connect to the global pool and the CERN pool, and that's how they try to acquire resources. So we talked about the grid mesh topology, which was introduced in LS1. So before that, in Run1, we had this hierarchical model of CMS grid sites, where the original design was like in tier 0, we had the data where it comes from and the first data reconstruction. The tier 1s were the national centers, which were used only for simulations and data reconstruction. And tier 2s were the regional centers, which were used only for analysis. But CMS wanted to be a little more flexible, and we were able to achieve better overall throughput and better resources with the new mesh topology. So the mesh topology is basically where all the tier 1s, tier 2s can communicate with each other and different tiers. So it gives overall more flexibility and a better throughput of the whole system. So this is the graph which was made through the actual data used from Run1 till LS2, and it shows how the continuous increase of CPU utilization has been happening from 2010 to 2019, which is the LS2 right now going on. And these are the estimates of the CPU which are required for Run3 and HL-LHC. So the dotted line that you can see is actually the um, the resource estimates, which are the common resource estimates with the 200 PU. For more insights about workload scheduling and provisioning of CMS offline computing, a colleague of mine will be giving a talk on 31st of July. So you can tune in for that. The second main important factor of the growth and evolution is data management. So during Run1, we had our own software called FedEx, which was developed by CMS, and we used to use it for managing the data. There were different group and site managers, which had to do a lot of manual work during Run1. During LS1, we came up with dynamic data management and the Extrude 3 for AAA. So I will be telling you a little bit more about Extrude 3 for AAA in the next few slides. Then we also had a major upgrade in FedEx, which was using FTS3. And we separated the disk and tape endpoints for tier ones. During Run2, we had a complete dynamic data management software, which was called Dynamo. We had advanced Extrude D monitoring, and we also had the Extrude D write support implemented during Run2. During LS2, which is right now, we have been migrating from FedEx to Ruscio. So Steve already talked in the last talk about Ruscio. And we have been doing transferring of data via Extrude D. Then we have all these things being monitored on the Monet Grafana infrastructure. And we started working on operational intelligence. The plans for Run3 and HL-LHC are basically to improve the data management with more intelligent algorithms for efficient utilization of disks and tapes. The second is to migrate from certificates to tokens for authentication. And CMS is also working to achieve the same functionality of dynamic data management through Ruscio. So what this Extrude D and AAA we have been talking about is basically the remote data access. So AAA stands for any data, anytime, anywhere. It's an efficient remote data access and important for the flexibility and increasing throughput. All the CMS applications input-output extended to include remote reads. The present technology choice was Extrude D-based storage federation, and the site published the storage inventory to regional redirectors. The central production uses AAA routinely to read input files for data in Monte Carlo workflows, and the physics analysis, data detector commissioning, and other users also save time because no one needs to wait for the data to be transferred locally before they start running their jobs. So you can see the graph on the right-hand side, which shows that the successful remote read has been better than the successful local read. And we had a very low failed remote read. So that's a great thing which was implemented during LS1. The dynamic data management, so the Dynamo software that we use right now for dynamic data management manages about 118 petabytes of disk space, and it uses all the tier, like it manages the space on tier 0, tier 1, and tier 2 sites. So DDM works on three main policies. The first one is data popularity. So it basically creates more replicas for popular data sets and lower replications for less popular data sets. The second is the disk usage level. So we try to keep a safe level and use the available disk space. And the third one is a set of policies, which is like, for example, keeping 2 copies of a particular data at different sites, 3 copies of a particular data at other sites, and so on. So these are the estimates for Run3 and HL-LHC for the total disk and tape which would be required. And here also you can see that the dotted line has been continuously increasing, and we are going to reach exabytes of data on disk during HL-LHC. The third and the last point for the growth and evolution of data product of CMS offline computing is data production. So during Run1, there were a lot of manual work involved, where a lot of people used to do manual submission of workflows using prod agents. So this prod agent is basically the prod schedules, which we talked about in slide 6. Then the data reconstruction started during Run1 because, of course, the data started coming in Run1. During LS1, we migrated from prod agents to WM agents, which was a major upgrade. And we started having the remote data access, which allowed decoupling of workflows. So the remote data access, which we just talked about. And during Run 2, we had a recovery system implemented in the WM agents, which helped a lot because we don't have to start running the jobs from scratch. If a few of the jobs were failed, we just used to run the failed jobs again. Then a lot of manual submissions, which used to happen during Run 1, was all removed during Run 2 with the help of Unified, where we used to automatic assignment and management of workflows. Then we introduced step chain workflows during Run 2, and we started moving towards open source technologies like MariaDB. During LS2, we have been working on the automation for resubmissions and log analysis, integration to Ruscio, and monitoring all the workflow management through Monad Grafana and introducing Kubernetes. The plans for Run 3 and HL-LHC is to further improve scalability, shift to more community-based solutions for web frameworks and databases, increasing code currency, horizontal scaling of Kubernetes, and the better usage of data availability. So the decoupling of workflows, which we had with the help of remote data access during LS1, earlier, these particular types of data used to run only a particular site, but with the remote data access being available during LS1, we were able to run different data tiers at different sites. And so you can see that the dotted line shows how we were able to integrate this connectivity in LS1. As of LS2, CMS has more flexibility and everything can run everywhere except the analysis workflows at HLT. So this was a big gain in flexibility during Run 2. And all of these data tiers were handled by DDM. For more insights on Kubernetes, how we have been implementing in CMS, we have a talk from one of my colleagues tomorrow in the morning, talking about Monad Grafana, which we have been implementing in almost every part of different structures of the CMS offline computing. So this is just a screenshot of the overall view where you can see we have been monitoring analysis, production jobs, tier 0 jobs, and the submission infrastructure, and almost everything which we can try to monitor through Monad Grafana. The challenges for the future are moving towards heterogeneous computing, supporting continuous development and operations, computing and the storage resources to meet the needs of the future, and developing more intelligent systems for operations. So this brings me to the end of the slide, although this is just the beginning and we will continue to evolve and provide physics better than ever. Thank you.
So thank you. This was a very nice summary. I will call for questions now. Does the audience have any questions here? No, I guess it was there. Oh, we do have.
Easy ask, Concetio. Just raise my hand.
Go ahead.
All right. So thanks for this talk, Sharad. You mentioned in several places Kubernetes, and then you pointed also to a talk that will exploit how you use this for CMS web. Is there any other use cases that you are currently exploring? I mean, what are your plans? Is this the only one that you are
in CMS web, we have a lot of different things. It's like all the different services which we use in CMS. And that is the whole thing called CMS web. And we are trying to implement Kubernetes on all of these. So my colleague Imran would be able to give you a better insight knowledge of what they have been up to, because I don't want to kind of destroy his presentation, which is tomorrow.
Okay, thanks.
Okay, Steve, do you want to ask your question?
I was going to ask a related question, namely, have they come up with any difficulties in using so much Kubernetes at this point? Or were there any adoption hurdles that they'd hit? But I guess I should see the next talk tomorrow And you'll tell us that.
Yeah, I think that tomorrow is also at a pretty inconvenient time for the US time zones. So you might have to see it on the replay session. But yeah, I think that'll be interesting. I happen to know that, you know, the other uses of Kubernetes, you know, would be in provisioning on the sites. And so far, CMS has had a little bit of a hands-off on that, where, you know, there are R&D projects for that, like at Lincoln, Nebraska, they're using Kubernetes together with HT Condor to schedule analysis facility type of notebook jobs. We had a presentation about that at PyHep, which is also recorded if you're interested. But yeah, it's oh, I see that Danilo, who's really in charge, wants to ask.
Yes, I think, yes, Liz, you're right. For what concerns, well, the usage, I fully support the invitation of Sharad to the talk of tomorrow by Imran. Clearly, Kubernetes will become, and we're working hard to make it happen as soon as possible, the backend for the internal services of the experiment. Clearly is a technology which is on the rise. I mean, at HL-LHC, there was an entire track dedicated to this and full of talks and nice contributions. Clearly, if a site decides to provision resources through Kubernetes, I think it will be most transparent for the experiments. And I mean, for example, CERN presented at HL-LHC a measurement that they did in order to remove some of the overhead, which is very little from the VMs, but provisioning batch nodes through Kubernetes and gaining something which was about 5%. I mean, if you go and look at the slides. So it's something that can be used transparently once it's provided by sites. And internally in CMS is really the portfolio of internal services of the experiment, moving back and taking advantage of the elasticity of this new technology.
Yes, very good, thank you. I don't see any other questions. If that's the case, then we are ending exactly on time here. So I want to thank everybody, and especially our last speaker. I guess we'll call this